Hello everyone. So we are in the unit of switched capacitance minimization. So already in the last unit we have seen different types of power dissipation techniques, and also we have seen different types of system level approaches and device level approaches. So in today's class, so already this bus encoding also we covered in the last class. So in this bus encoding, so we have different more techniques. Those are nothing but gray coding, and another one is one hot coding, and another one is T naught coding, and another one is bus inversion coding. So these different types of coding techniques that should be used to reduce the power dissipation at the input and output transmission of the data. So while in the system level, whatever we designed a processor or we designed a microcontroller. So when that processor or the microcontroller will be operated under low power, low power mode. So even the processor internally, we have different combinations of devices within a device. So for example, we can consider a CPU. So in this we have mainly different type of devices. Those are nothing but input device and the output devices. And also internally we have also have within the CPU we have ALU and different type of processors and different type of memory devices and different type of controlled devices. So these devices uh, will communicate uh, whatever the devices placed within the system. So those devices will be communicate with help of some input and output combination of the data. That means whatever we are expecting different operations from that device, so that is able to process. That means the communication will be performed in between the whatever the devices placed within a system. So in that system, that means however we are transmitting the information from one place to another place. So in the same way, that whatever the devices will be placed within a system, so either it may be a processor or controller, or either it may be a combinational circuit or sequential circuit. So the operation of that circuit may depend on mainly the input and output processing of the data. The inputs and outputs will be proper inputs we have to given to that device. So then that will be give some output with respect with the inputs. So in this bus encoding technique, so here whatever the devices, that means whatever this VLSI chips will be manufactured with MOS devices, metal oxide semiconductor devices. So during the design of these MOS devices, so we have some of the intrinsic capacitances of system level buses are usually, so these buses or these devices will be manufactured with help of the MOS devices. So due to that, so these systems have the intrinsic capacitance values. There will be very high magnitude than that of the internal nodes of a circuit. So we have some of the nodes within any type of IC. So these capacitances will be the magnitude of this capacitance value will be very high compared with no internal nodes of circuit. So this whatever this capacitance takes place, so definitely it will consumes some amount of power is dissipated for transmission of data over input and output pins. So whenever we are processing the information or the data from one pin to another pin of any type of IC. So definitely to process the data from one end to another end, so that will takes or consumes some amount of power. So that amount of power, so we have to save some of the significant amount of power uh, to maintain or to reducing the number of transactions. That means the number of switching activities at the processor's IO interface. For example, consider, so if you have an automatic system, automatic washing machine, so that will automatic remote controller will reduce the number of operations. So that will be reduce the number of operations. So that will based on that we have consume the power. So the same concept will be implemented within the IC operations also. For example, consider in our home, we have an automatic AC system. So initially our room temperature may be some 31 degrees or 32 degrees. So whenever our system is worked with our AC is worked with automatic, that means whenever the room temperature will be slows or goes down to some 23 degrees or 20 degrees, so automatically the AC will be turned off. So then automatically we save the power. We save the power in terms of in view of whatever the electricity department will be generated from whatever the department generated, the power will be saved with help of this automatic system. So at the same time, so we doesn't have any automatic control. So definitely whatever the manually uh, we have to switch off that button. So up to switch off that button, so that continuously uh, running that mission or running that equipment. So due to that, that will takes or that will leads to the device that system will consume more power compared with the automatic automatic system. So here in this also, whenever we are processing the information from one device to another device, so based on that switching activity of the device and the processor's input and output interface, so whenever we control this type of activities, so definitely we have to reduce reduce some amount of power dissipated for transmission of data over the input and output pins. So to reduce that switching activities, so we have to use different types of encoding techniques. Those are nothing but so that encoding can be used either to remove undesired correlation among the data bits as it is done while doing encryption, or also that will introduce controlled correlation. So to maintain the limited switching activities, so we have to use some of the encoding and the decoding devices. So this will reduce the switching activity, and also it is necessary to increase the correlation among the signal values transmitted over the IO pins. So here these coding schemes are mainly divided into two types. One is the non-redundant techniques and another one is a redundant technique. So in this non-redundant coding, so an n-bit code is translated into another n-bit code. So in case of the non-redundant code, so we have some of the code. So that code is translated into the another n-bit code, that is m is equal to n, and the 2 power n code elements of n-bit are mapped among themselves. So whenever we are adding that uh, n-bit code with required code elements, so then that will definitely reduces the additional lines required for to send the data data from one device to another device. So in this case, the non-redundant coding is done based on the statistics of the sequence of words. So based on that, the switching activity is reduced when we are using this non-redundant coding in between the encoder and decoder. So in non-redundant coding, so mainly we have n bit and bit code, and that is translated into another n bit code. So that is n is equal to n is equal to m. So this for n and m will require 2 power n code elements. For example, m is equal to 3 or n is equal to 3, m is equal to n is equal to 3. So that is 2 power cube is equal to, so 8. So that code will require 8 elements to transfer the data from one side to another side, or one pin to another pin. So here that is about redundant code. And coming to sorry, that is about non-redundant coding. So coming to redundant coding technique. So in this redundant coding technique, so we here in this redundant coding, we must and should require additional lines are used for sending the data. That means so in case of the non-redundant coding, so where the code elements and the data will be equal to the whatever we are transmitting the bits from one end to another end. That means m is equal to m is greater than n. M is greater than n. That means here 2 power n different n bit words are mapped to a large set of m bit 2 power m data words. So uh, to perform these operations, so we have two alternative choices. One is the encoder and decoder may be a memoryless or may use memory elements for the purpose of encoding and decoding. So if an n bit word has an unique m bit code word, so then neither maybe encoder or decoder requires the memory. So another possibility is, so here we have to use a static one to many mapping 2 power n unique code words to 2 power m code words. So the current state of the encoder selects a particular m bit code word for transmission, several alternatives for particular n bit data word. So in this scheme, so we require the memory, and the decoder can multiplied can be that may be consisted without memory. So in case of the redundant coding, so we have to use two alternative choices. Those are nothing but, so we should use with memory or without memory. So to process the data from one end to another and one end to another. So for this, so we have to implement those redundant and non-redundant codings in two formats. One is the gray coding, and another one is inversion gray coding, and another one is inversion coding, and another one is coding, one hot coding. So this gray coding, it is one of the most popular example of non-redundant encoding scheme. So this the gray coding, so we have to use gray coding that will be implemented in any type of system. That means in any type of device, so that will consumes the low power category. That means that will reduce the number of transitions, that will reduce the number of transitions. So here this gray coding technique is one of the most popular example for the non-redundant coding. So whenever we see this gray coding operation. So here we have a truth table for this gray coding. We have a truth table, that is the binary and gray codes for different decimal values. So here we have the decimal value from 0 to 50 and the binary code. So that same, the decimal value will be represented in a binary format with a 4-bit binary format. That means 0 represented with 4 zeros. So already I think you know about 8421 code. By using 8421 code, so we have to represent any for any decimal value. So we have to represent the decimal value with a equivalent binary code, with a equivalent binary code. So that binary code will be converted into a uh, specific gray code. Converted into a specific gray code. So here we have to write the equivalent code for the decimal value 0 in the binary code and the gray code. So this gray code will be implemented with the help of XOR operation, a simple two-input XOR operation. So already we are very familiar with this XOR operation. So what is meant by two-input XOR operation means, so whenever we have that we have a two-input XOR gate. So if that two-input combinations, whenever the combination will be, the XOR combination will be odd number of ones. So then the that will gives one, that will gives one, and the remaining time. So if that even number of ones or even number of zeros, so that will gives the output is zero. Output is zero. That means, so in case of the same input, so both the inputs are same. So at the time the output of the XOR gate will be 0. So if the different inputs, that means if the A is 0 and the B is 1, so at the time the XOR operation, the XOR output will be 1. XOR operation will be n. So the same thing will be implemented to convert the binary code to gray code. Binary code to gray code. So here you will see for the equivalent decimal value is 0. Equivalent decimal value is 0. That for that equivalent 0, the equivalent binary code is 4 zeros. 4 zeros. So it is simple 8421 code. So this binary code will be converted into gray. How we will convert binary to gray code means, so here first bit of the binary code and the first bit of the gray code is same. So we have to take the same bit as first bit of the gray code. First bit of the gray code. So next after that, after that step, so we have to do the XOR operation in between one one bit of the binary code to next second bit of the binary code. One bit of the binary code to second. That means 0 XOR of 0 is 0. And next second bit of the binary code to third bit of the binary code is, that means 0 uh, 0 XOR of 0 is 0. So next from third bit to fourth bit, 0 to 0 XOR of 0 0. So by following that, by doing that, so we have to write we have to convert the binary code to gray code. Binary code to gray code. So here we have to remember 2 points to convert from binary to gray code. So the first point is whatever the binary code, first bit will be same for the gray code. Same for the gray code. So as it is, we have to write or we have to take first bit of the binary code is equal to gray code. So after that, so we have to perform the XOR operation. XOR operation means 0 XOR of 0, 0 XOR. That means 2 0 XOR of 0 is 0, and next 0 XOR of 0 is 0, like that. So again, for example, we have to see for two two binary code, two binary code, that is a decimal two value. For this one, so we have the first bit is 0 0. So next 0 XOR of 0 0, 0 XOR of 1 1, and 1 XOR of 0 1. So when by writing that, so for binary code, for this 0 to 15 binary code, so that will take 30 transitions, 30 transitions. That means so we have that may require 30 switching activities to implement or to process this data from 0 to 15, from 0 to 15. But here for the gray code, so whenever we observe from the 2, so that will the gray code will changing the position. That means changing the position. So for same amount of data, so in gray code, so that will take 15 transmissions, 15 transitions to transmit the data from one end to another, and from one end to another end. So that is the difference. That is the difference between from the binary code to gray code, from the binary code to gray code. So here, whenever the number of transitions will reduces, then the power dissipation of the circuit is also decreases. The power dissipation of the circuit is also decreases. So that's why. So here we have to see uh, whatever in what way we are establish the gray code for in between encoder and decoder. So in case of gray code technique, so mainly the gray code technique is used for is that will be implemented in between the encoder and decoder, two input exclusive OR gates, two input exclusive OR gates. So here, by using these gates, we have mainly reduce the power dissipation of the circuit, the power dissipation of the circuit. So here the gray coding has been applied to the address lines for both the instructions and data access, for the reduction of switching activity, for the reduction of switching activity. So whatever the data we are processing from one end to another end, so here we have to apply the gray coding for the to the address lines for the both instructions and data access to reduce the switching activity, and also based on that performance of the device. So that is also takes place in view of the simulation. So that results there is a significant reduction in switching activity on the address bus. So that will be performed because of instructions are fetched from sequential memory locations. So here, when a branch instruction is executed, so here that will leads more than one transition, even the gray coding is used. So whenever this number of transition will reduces, and the frequency of occurrence of branch instructions uh, is also maintained from 0 to 15. But that means from every value we have to maintain a specific frequency to perform a specific operation, a specific operation. So to implement whenever we are maintaining this type of arrangement in any type of device, when any type of device, so that will reduces the power dissipation of the circuit, the power dissipation of the circuit. So how it will be reducing the power means based on the number of transitions will be reduced when you are maintaining proper gray coding technique in between the encoder and decoder. So in case at the input of the encoder, so we are giving the binary code, that means 0 to some n minus 1 codes. At the same, the gray code is also follows from Z to Gn minus 1. So in between the encoder and decoder, so we are reducing the number of transitions. So after the decoder, so we are getting the original data bits. That means whatever we are sended from 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 the encoder to decoder. That is the main uh, operation involved in the uh, in between involved in gray coding technique. So and one hot coding. One hot coding. So it is also one of the example for redundant coding. So here in textbook, it is a print mistake, non-redundant. So it is one hot coding is example for one hot coding. It is the example for the example for the redundant coding. So here in this bus inversion code also, we have the sender device and the receiver device, and in between sender device and receiver device also, we have to maintain some encoder and the decoder. So in the sender chip and the receiver chip, we have the sender and the receiver. In between the sender and receiver, we have at the sender side we have the encoder device. At the receiver side we have the decoder device. So in between those encoding and decoder, so we have to maintain 0 to 2 power n minus 1 operations, 2 power n minus 1 operation. So this one hot coding provides reduction in the switching activity when the data sent over the lines are sequential and highly correlated. So this is also used for to reduce the switching activity between the sender device to receiver device. And this will the switching activity of this will be reduces whenever whenever we send the data in a sequential manner. So then it will be reduces the power dissipation of the circuit. So here in case of the data sequence are random in nature, so the gray coding does not provide reduction in the switching activity. So in this case, if the in the one hot coding, if the data may be random, so it will also provides some of the one hot coding technique to reduce the power dissipation of the circuit. So that is about different techniques used in switched capacitance minimization. So we'll continue the remaining topics in next class. We'll continue the remaining topics in next class. Thank you for watching this video.